So I don't need to convince you about how exciting and interesting data compression is, because that's why you signed up for this course, I assume. And, even if it isn't, then I'm sure that I did an amazing job of convincing you of that in the first lecture. But the problem is, before we can get around to all of the exciting and interesting things that we're looking forward to, things like implementing compression schemes or designing our own compression schemes, we have to resolve a bunch of annoying philosophical questions like, what does the word compression mean? And when am I actually achieving compression? When am I doing compression properly? So it's really important to me in this course that we get to discussing real compression schemes as soon as we possibly can, because I want to highlight what I consider to be one of the core dilemmas of data compression, which is that on the one hand, we want to sit down and work out clever tricks we can use to save space. So in a sense, on paper or theoretically, develop ideas for compression. But on the other hand, we also have to be able to implement them. We have to be able to write code, write a computer program that can actually produce a sequence of zeros and ones that is shorter than what we started with, actually achieve compression. And it turns out that those two pieces, the theoretical part of coming up with clever tricks and the more applied part of writing code or implementing it or turning it into zeros and ones, often those are in conflict. We can come up with all sorts of clever tricks, but when it comes down to it, we may not actually be able to save space using those tricks, even if it seems like we can. I'm going to show that off even in this lecture, but then I immediately want to jump in the next lecture to talking about an actual compression scheme. And then we'll come back and talk about more theoretical things later. I think having the context of seeing the compromises that had to be made for an actual compression scheme will provide a lot of important context. Okay, whatever. Before we can do any of that stuff, we do still have to figure out what the word compression means. So here is a snippet of English text. It is the first sentence of A Tale of Two Cities by Charles Dickens, a book that, for full disclosure, I have not read, although I have read the first sentence or so of it. I've chosen this because this is an actual English sentence. This is an actual piece of English text. As you know, often the question of which inputs somebody is choosing when they're demonstrating an algorithm or other thing in computer science to you is something that you should be suspicious about. So for example, if you think back to a course like CSC 225, Algorithms and Data Structures, it would be possible, if I chose inputs correctly, to make a case that bubble sort is the best sorting algorithm asymptotically. If I just use a case study of a few inputs and don't do analysis, I could say, look at how fast this algorithm is on all of the inputs that I chose. And you should know better than to believe that. Obviously, without performing worst case analysis on an algorithm and doing that rigorously, you can't trust what somebody says about the performance of an algorithm or a computer program on some selective set of inputs, especially if they have a vested interest. Now, it's a lot harder to do that in compression for reasons that are going to become clear about halfway through this lecture. We can't really talk about worst case inputs. We can certainly talk about pathological cases, and we're going to do that in this course, but we can't so much analyze some compression scheme to see what the worst compression it's going to provide is, and we'll see why that analysis, although it's possible, doesn't really yield any useful results later in this lecture. So often what we do in compression instead, when we talk about sample inputs as a way of demonstrating a scheme, instead we talk about choosing actual data, choosing inputs that are likely to be encountered in practice, not inputs that I've contrived for the sake of proving a point. Now, it's still possible, and this is true of all courses you take, but certainly of this course, that when I put an input on a slide, for all you know, I do have an ulterior motive. So you should use your critical thinking skills carefully and not necessarily just believe everything that I say. If everybody just believed everything that I say, I would probably turn to evil very quickly. So be careful about that. It's a good thing to have a certain healthy level of suspicion about anything you hear in a course in university. That's why you have all those critical thinking skills. Whatever. In any event, this is certainly an actual piece of English text. It's not a sentence that I wrote for the sake of proving a point. Maybe I cherry-picked it, but it's actually a sentence from a reasonably well-established piece of English literature. And my goal is to take this 416-character piece of text and find some way of storing it in fewer characters, or in fewer bytes, or in fewer symbols, as you'll hear me use the term in later lectures. So we often want to separate ourselves from this notion of always working in bytes. We instead talk about bits or symbols. So in the first lecture, we talked a lot about this idea of leveraging the extra bandwidth that we're not using. So if I store this snippet of text, if I paste it into a text editor and save it as a text file, then each individual character will be stored as 1 byte. So each character will be stored in 8 bits. The number of possible sequences of 8 bits is 256, so that would be 2 to the 8. And we can observe that in this snippet of text, I'm not actually using all of the possible 8-bit sequences. I can't be, because there are only 28 distinct characters. And to be clear, those characters are a bunch of different lowercase letters. Not every lowercase letter, but a bunch of different ones. So there's a lowercase letter, there's a lowercase letter, here's another lowercase letter. Okay, a bunch of different lowercase letters. There's also various occurrences of the space character, just the space character. There are no tabs, there are no new lines. So these are actually, these line endings are just to fit the text on the slides. There's no new lines here. And there is also punctuation, but just one form of it, just a bunch of commas. So there are a few uppercase letters, a bunch of lowercase letters, spaces, and commas, and there are a total of 28 distinct characters in this 416 character sequence of text. So if I choose to store each character in 1 byte, well, certainly that's convenient. That's why we use 1 byte for each character in general in our text files. But I am, in a sense, sort of wasting space. I don't actually need 8 bits to represent all 28 distinct characters that appear here. And so I could observe that maybe this is a fruitful avenue to save some space. If I use fewer bits, maybe I save some space. It's the same idea that we had in the first lecture. In this lecture, I want to explore why, although that's a good instinct, it's a little bit easier said than done. It's one thing to say I could save some space. It's another to actually write a compression program that demonstrates that shows me that the space is actually being saved. So it's a clever idea, but there are a lot of headaches in implementing it. But if we run with it, we could observe that if I have 28 possibilities, how many bits do I need to represent that? I want as few as possible. Well, if I try 4 bits, so 2 to the 4 equals 16, that's not going to be enough. And if I insist on representing each character separately, then each character needs to be represented in some uniform number of bits. So I guess I'll have to use 5 bits. So there are 32 possibilities if I use 5 bits. Okay, well, that's good enough. I mean, that's certainly better than 8 bits in terms of not wasting possibilities, because if I have 28 characters, only 4 are going to be left over if I choose to represent each character in 5 bits. Okay, so that is definitely an improvement. I've gone from 8 bits down to 5, so a savings of 3/8, so about 37%, I guess. And if we all agree on some way of encoding the particular selection of 28 characters into 5-bit sequences, then this is indeed possible. And it's in this agreement that we're actually sort of cheating by the rules that we're going to define later in this lecture. But if we decide on some encoding and we both agree to it, so I can be the compressor, you can be the decompressor, if I convert my plain text by taking uppercase I and generating this bit sequence and lowercase I and generating this bit sequence, and then later, so let's actually do that. So if I want to encode, let's do, I'm going to encode the word the. Okay, so THE, well, how do I encode the letter lowercase t? Well, that's this. So my bit sequence is now going to be 10111. All right, the letter H is now 01101. Okay, that looks good. And the letter E is 01010. So I can be the compressor, I can use this table to perform this encoding, you can be the decompressor, and I'll leave it as an exercise, but I'm sure you can see that you could take this bit sequence and go in reverse. If I write 2 computer programs, one to perform the forward encoding, so to take each character in 8 bits and encode it into 5 bits, and a second program to take each character in 5 bits and go backwards in my table and recreate the 8-bit version, then indeed I can apparently save space. Now, the problem is if I write programs that only work with this particular encoding table of these 28 characters to 5 bits, well, arguably, I'm not really writing a compression tool. I'm writing a purpose-built transformation designed for this one snippet of text. And that's one of the things we sort of have to circle around a bit before we can understand how best to view that as a constraint. Whether that's cheating or not, or what extra measurements we need to make to decide whether we're achieving compression. But there's still that word compression, and I still haven't really defined it. So this idea of encoding this text with 5 bits instead of 8 bits because it was motivated by trying to save space, well, that is an example of a compression scheme. Well, I've put the word compression scheme in bold. Does that mean I'm defining it? No, not quite yet. Just give me a few more slides. I will give a nice formal definition, nice and crunchy, with some Greek letters even, but not quite yet. So this is an example of a compression scheme, going from 8 bits to 5. Obviously, the goal of a compression scheme is to reduce the amount of space needed to store a piece of data. Okay, that's the goal. Really, that's an aspirational goal. We'll notice later that mathematically, there is one thing that's higher priority than reducing the amount of space, and that's preserving the integrity of the data. So the highest priority of a compression scheme, at least as I'm going to use the term, is preserving the integrity of data. And that's because, in general, if I'm compressing arbitrary data, so if you hand me a bunch of binary data, I have no idea what it is, could be text, could be an image, could be an executable file. If I compress it and then later decompress it, I want to leave it intact. I want nothing to be changed. And it turns out that actually that isn't universal. There are times in compression where I don't mind a few errors occurring. And so before I can fully define the word compression, I want to talk a little bit about that. That's also something in this course that we have to explore from both sides. So an example of that would be, suppose that I want to explore ways of saving space. So anything I can do to reduce the bandwidth that I need. Well, here's my original data. I could try a transformation. Now, the transformation I'm going to do isn't itself going to save space, but maybe it's going to produce some data that's easier to store in less space. So this transformation is going to aid some future compression attempt. And maybe you can appreciate why it might do that. My transformation is going to be, I'm going to take every vowel in my input and just delete it and replace it with a placeholder. So every time I see a vowel, I'm going to replace it with an asterisk. And then if I count the asterisk as one of the characters present, I end up with this transformed excerpt. And the transformed thing still has 416 characters, but only 23 distinct ones. Now, that still means I need 5 bits if I'm obsessed with this bit reduction idea, but because there are fewer distinct characters, I may have other options for saving space. I have reduced, I guess, in an informal sense, the complexity of the data. Now, we will formalize the complexity of data, something called information, later in this course, but I have in some way reduced the complexity of the data, at least in an intuitive sense, by deleting all the vowels. Okay, that's one thing. That actually wasn't the point I intended to prove. The point I intended to prove is, suppose you hadn't even seen this. If you had never seen this excerpt before and all I gave you was this thing, would you be able to read it? If I said, this is English text with the vowels removed, could you tell me what it says? You know, I'll bet your brain, even if you're not familiar with the original excerpt, could piece together most of these words. Because your brain, human brains, are really good at pattern recognition. So you see the word th star, and you know that the star is supposed to be a vowel. Well, I mean, it's probably the word the, because that's an extremely common English word. And I can only think of really one other English word that has th followed by a vowel, and even that's a little bit of a borderline case. And so once you have the word the pieced back together, it's easier to piece back together the words around it. And so even if I delete all of the vowels from the text, you might still be able to read it, which means that this idea that I need to preserve my data isn't necessarily universal. Maybe there are times I am willing to sacrifice a bit of accuracy because whoever's perceiving the data, so if a human, for example, is reading it, they have a certain amount of error tolerance. And so we have to define that. We actually have to talk about that in this course as well. When am I allowed to make mistakes, or when am I allowed to deliberately destroy data versus when am I required to keep it intact? So most of the course, and the beginning part of the course especially, so up until I think early July, this course is going to be spent on lossless compression schemes. And in general in this course, in all of it, even in July, if I just say the word compression scheme with no qualifier, I mean a lossless compression scheme. So in a lossless compression scheme, the input data that goes into the compressor and what comes out of the decompressor must be identical. So no compromises are allowed. The data must be preserved 100% intact, or it is not considered to have been compressed successfully in a lossless compression scheme. No differences are allowed between the ultimate result of decompressing the data and the original source data. Nothing. It must be a bit for bit identical facsimile of your original input data. The alternative to that, of course, if we say lossless, well, okay, so what if I am allowed to lose something? What if loss is allowed? Well, we end up with something called lossy compression. So lossy compression is where you can still use all the techniques you use in lossless compression, which is why we're going to cover lossless compression first. But in lossy compression schemes, you are allowed to deliberately delete part of your input data for the sake of saving space. And so an example of a lossy compression scheme is JPEG compression, which is used for images. Now, I should add one thing you might observe with me discussing JPEG, if you know a bit about compression schemes already, is that JPEG is actually pretty old. It's more than 20 years old now, as of 2023, and there are a lot of other image compression formats that have come into being since then, many of which are widely used. And yet, for some reason, here I am talking about JPEG compression. And that's a trend you're going to notice in this course. I'm going to talk about a lot of schemes that actually have been around for a long time, even later in this lecture. A lot of our comparators, when we compare our own schemes to existing ones, will be pretty old. And that's all the more reason why we should be able to compete with them. But it's also because even though JPEG is an old scheme, it has been adopted so widely and it is still used so widely that it is still a very current thing to compare against, although there are more recent schemes that are also widely used. JPEG is pretty much ubiquitous, and that's helped by the fact that a lot of compression techniques for images and video are supported by hardware, and therefore because of the relatively slow-moving progress of dedicated hardware for things, even old schemes are still in wide use. So in JPEG compression, which is a lossy compression scheme, you are allowed to provide a parameter, so we call this the quality parameter, that tells the compressor how much data it should try and destroy. And the idea is often when you're working with lossy schemes, the reason why you need to be allowed to discard data is because you are constrained in how much data you are allowed to represent. So one easy example of that, I think, in a modern context, because you're dealing with that example right now as you watch this video, is streaming video compression, where often streaming video is limited to a specific amount of space per second, a specific number of bits per second, because of bandwidth available on an internet connection or whatever, across some broadcast channel or anything else. And because of that, because you could be limited to some number of megabytes or megabits per second, the compression scheme needs to do whatever is necessary to make the data small enough to fit within those constraints. And in general, with JPEG and other lossy compression schemes, there can be two different options. One option is telling the compressor, I need you to make this image smaller than 1 megabyte. Another option would be telling the compressor, I authorize that you make the image maybe 70% of its existing quality, or 20% of its existing quality. I would argue that both techniques are essentially setting a quality parameter. They're telling the compressor what compromise to make between quality and space. So one way of compressing JPEG files is giving it a quality parameter between 0 and 100. This image over here is 500 pixels wide by 335 pixels high, which is not a high resolution. That is a very low resolution by modern standards. The reason I've chosen it is one thing, to keep the size of the slides down, but also because we want to use this test image later and we don't want to wait too long if our scheme is slow. This image is 500 by 335. We'll see this image a lot in this course. And I've stored it, the representation on the left is a lossless image format. So the PNG format is lossless. And in fact, we're going to study some of the underlying lossless compression techniques used by the PNG format in great detail in this course. Over on the right, I have taken the same image and I have stored it as a JPEG image. And I've set the quality parameter to 100. So I've told it, reduce the quality by basically nothing, so as little as possible. It is still allowed to throw data away, but I'm constraining it against the upper end of that. So very little is being thrown away. The result is 261 kilobytes versus 266. So a very modest savings. Now I should add, and we'll get back to this, but 266 kilobytes is not the true size of this image. If this image were stored uncompressed, it would be a great deal larger than that. But for the sake of a fair comparison, I suppose I should be comparing lossless compression against lossy, not fully uncompressed against lossy. So in these lossy compression schemes, this quality parameter allows us to control the size more than we would with just lossless techniques, because often with lossless compression, you don't have much of a choice. If you have to preserve the data 100%, then you might be able to achieve compression or maybe not, but you have very little control about how much compression, beyond things like how much CPU time or memory am I willing to spend. But even then, if you're willing to spend days of CPU time, there's only so much lossless techniques can do. Whereas with lossy techniques, you can set this quality parameter to say throw away more information to make the size smaller. And I'll illustrate here that if you take a look at the version where the quality is set to 100, and where it's 261 kilobytes versus quality set to 25. So I'll flip back and forth one more time. Those of you watching this on YouTube, I don't know whether you can see the quality difference. Maybe go pull the slides up separately, the posted version of the slides. Here I've set the quality parameter to 25, and I get a 17 kilobyte image. So I'll do one more round, 261 kilobytes there, 17 kilobytes. There are noticeable differences. The most noticeable differences happen sort of around here in my mind. At least that's where my visual system detects them. I have managed to save, about 244 kilobytes. So I've reduced this down to about 7% of its previous size. And I've thrown away a bunch of data, but it's not really obvious to a human viewer. And I would argue that if you'd never seen this, and you'd never seen the version with quality set to 100, if I just showed you this image randomly outside of the context of image compression, I'll bet that you wouldn't be able to notice the quality problems because you wouldn't know to look. I mean, the quality problems are there, but they're so subtle that you probably don't detect them on first glance unless you know that they're there, unless you know to look for them. So I've been able to save 240 kilobytes by reducing the quality significantly, but notice how this lossy compression scheme is clever enough that the information that it discards is stuff that I don't notice. So in particular, consider the fact that a human viewer looking at this, looking at a photograph of a pear, probably focuses most on the delicious pear in the middle. And although there has been a quality drop in the delicious pear over on the right, much of the quality problem has been relegated to areas where the human visual system isn't going to look. It's not going to pay that much attention. So underneath the pear, we have this background, which is sort of blurry in the original image, and it appears to be grass, I guess, blurry, sort of out of focus grass in the distance. If you take a careful look at the compressed version of that, the JPEG version, there is something strange happening there. There is a loss of definition, a sort of blocky or pixelated appearance. But the compression scheme is clever enough, and it does this in an incredibly elegant way that we're going to see later in the course. The compression scheme is clever enough that I guess you could say it knows that this is the detail that a human is less likely to notice. So when we lose detail in this area, humans are expecting this to be sort of blurry, and therefore they don't focus carefully on it. But we can go further. We shouldn't we shouldn't just say, oh, I can reduce it to 17 kilobytes. Well, great. But let's see if we can go any further than that. So here I've set the quality selector to 10 instead of 25. And so we've gone from 17 kilobytes down to 8 kilobytes, essentially, 7.9 kilobytes. And here the quality difference, I think, is much more noticeable. Even if you hadn't seen the thing on the left, if you look at the image on the right, you'd notice there's something a little bit wrong with it. And actually, because JPEG is so ubiquitous, most of you have seen what we might call bad JPEGs a lot already in your life. You've already recognized sort of the obvious signs of overcompressed images. I don't want to call it a bad JPEG because JPEG is a pretty ingenious scheme. It's managed to take an image that even compressed losslessly is 266 kilobytes and bring it down to 8 kilobytes where I, a human observer, can still figure out what it is. It's a photograph of a pear surrounded by leaves with maybe some grass and sky in the background. The grass has pretty much been reduced to almost nothing in this version, and the pear is looking pretty pixelated, although it's not quite pixelation, because I usually think of pixelation as the result of scaling the image down, reducing the number of total pixels. Even though there's some blockiness happening in here, the boundary of the pear and the edges of the leaves are still pretty well defined. They're actually still pretty crisp. A sign that the JPEG scheme is really good at identifying which details can we lose without reducing the overall salience of the image, without reducing the parts of the image that the human wants to distinguish. So I've gone from, if we compare it to the previous version, 17 down to 8. So I've lost more than half of the total space, but I would argue that I haven't really lost half of the total quality. I can see a quality quality reduction, but I can still understand what the image actually depicts. If we go even further, if I set the quality to 0, then we end up with, I think, pretty much a mess. I mean, this is clearly a significantly reduced image. Like, it's pretty obvious that this has been over-compressed, that we've lost a lot of detail. But I would still call your attention to the fact that even though we've lost tons of detail, we've gone from 266 down to 3.5 kilobytes, and we've got the obvious effects of that, artifacts showing up everywhere, it is still pretty possible for me, a human viewer, to figure out what's being depicted. It's probably a pear, or I guess generously some other type of fruit, in front of something that I guess is leaves of a tree. It's a bit dicey, but I'm still able to actually understand a lot about the image. And that's a sign that JPEG is doing a really good job as a lossy compression scheme. Now, in any event, if I'm performing lossy compression, part of that is this clever selection of which details to delete. But then, once I'm done deleting information, if I'm writing a lossy compressor, I guess I'll also just run the resulting data through all of my lossless techniques. And so because lossy schemes usually incorporate all of this lossless stuff that we're going to cover in this course, we're going to cover lossy compression later. We're going to talk about all the lossless compression techniques and then talk about lossy compression to build on that. Okay, so I had a great visualization of lossless compression. I don't really have the same visualization or lossy compression. I don't have the same visualization for lossless that I have for lossy. So instead, we'll work with a table of numbers. So sorry about that. Our original snippet of text from a few minutes ago was 416 bytes in size if I store it in a usual ASCII representation. Were I to convert it to 5 bits, if we agree on that encoding table from earlier, then I can get that to 260 bytes. So of course, if I use 5 bits per character, it may not work out to be an even number of bytes, but I'll just round up to the nearest byte. I'll just pad it out to the nearest byte. So what's our comparator? Is that good if I go to 260 bytes versus 416? Certainly, I mean, it's better than nothing because 260 is less than 416. But on the other hand, how do I know? What's my barometer for whether I've achieved, amazing compression or terrible compression? So what I'm going to do in this course is use what I'm going to call the big 3 as our comparators. These are 3 very well-established compression schemes. And the reason that I think that they're important, the reason that I consider them our reference comparators, is that these are 3 compression schemes that if you are using any modern computer operating system, odds are it has at least 2 of these 3 in some form already installed. And so all of these schemes are pretty old by the standards of computer science as a discipline, where things move so quickly that something from last year is considered old in a lot of subfields of this discipline. But the reason that I'm using them is because they are still so ubiquitous. They are still used everywhere. In particular, all 3 of these are still used for package management by operating systems. So the first one, and the oldest of the 3, is called deflate. Deflate was originally invented as one of the components of zip files, of zip archives. So the designer, or the company, I guess, designing the first software to generate zip files created this scheme called deflate. Later, that scheme was excerpted, I guess. It was recycled into a different compression tool called gzip, which is widely in use on Unix-like platforms. Whereas zip originated in the Windows and DOS ecosystem, although zip files are still used in plenty of cases on Linux and Unix machines. If you've ever interacted with an archive file of the form tar.gz, then you have used gzip. So tar files are often considered a sort of compression adjacent thing, but the tar format is not a compression format. Tar is an archival format, a way of combining a bunch of files together into one file. And it's pretty common to create archives for the purpose of distributing stuff across the internet or whatever, and that's why usually we combine archiving with compression. Zip is a different form of archival format, so it's an archival format that integrates compression in a way that actually means that tar files often get better compression. If you first make an archive and then compress, you're often going to get better compression than you would inside of a zip file. Frankly, though, most of that's irrelevant to us because in this course we don't care about file archival, we care about compression. And we usually work on the model that our compression tools get one file as their input and generate one bit stream as their output. So deflate is identified with gzip and zip files. And it originated in the, I guess, early 90s. So zip files existed since the late 80s, the late 1980s, but they supported other compression formats. So I guess deflate came of age in the early 90s. Later in the 90s, this format called bzip2, and if you've ever interacted with an archive of the form .tar.bz2, then you've used bzip2. Bzip2 came of age in the mid-90s or late 90s. It uses a completely different pipeline of a combination of techniques than Deflate does. Broadly speaking, so present company excluded, where Deflate seems to be doing the best among the three, broadly speaking, bzip achieves better compression than Deflate in across a broad variety of different inputs. bzip2 also generally takes longer to perform compression and uses more resources, so it takes more CPU time and maybe uses more memory. This scheme, which I'm going to pronounce LZMA, so as a Canadian, as a proud Canadian, I generally pronounce this character correctly, that is to say, I pronounce it as Z. But unfortunately, for better or for worse, I can't be entirely consistent, so I'm part American, and when I pronounce certain acronyms, I just can't stand saying the Z. LZMA just trips me up. So I'm going to say LZMA. I'm so sorry. So those of you watching this, future generations out there, please try and pronounce things more consistently. There's nothing that can be done for me. I can't be helped. So LZMA came of age, I guess, in the early 2000s. And my first experience with it, at least, was in an archival format .7z, which was a program called 7-zip. It's now used in a variety of contexts. If you've ever interacted with archives with the extension .tar.xz or .tar.lzma, or just .xz by itself, or .txz or something similar, then you have interacted with LZMA. LZMA is a format that has some common ancestry to Deflate. That is, they both use similar techniques in certain ways. LZMA generally is designed to use a lot more resources because by the time LZMA existed, there were a lot more resources like memory and CPU time to go around. And broadly speaking, across a wide variety of inputs, particularly large inputs, LZMA often gets the best compression of the big three. There are plenty of other compression techniques out there. The reason I'm choosing these three as our comparators is, again, that you can find them as command line programs, as command line tools on a lot of operating systems right out of the box. If you install a modern Unix or Linux distribution, odds are at least two of these three are already installed as command line tools, and any that aren't installed are readily available. So it's easy to use them as comparators. And because techniques that are used today, I guess what you could call more modern compression schemes, are actually using many of the same techniques that these three use. They're just cranking it up and using more resources or something. So they're using longer search processes, or they're using more memory to store data. So this table is just the result of applying these three techniques to our original input sequence and comparing it to the size of the original data and the size of the apparent size of our 5-bit encoding. Notice that Deflate seems to do the best. And that isn't really because Deflate is generally better. That's because Deflate, I think, in my opinion, tends to be a little bit better on small inputs than the other two. Because, frankly, most compression schemes are designed for compressing inputs a great deal larger than 400 bytes. If I were to take the entire text of the book, A Tale of Two Cities, which comes out to be about 750 kilobytes, and for the sake of full disclosure, what I'm using here is the Project Gutenberg version of the text, where I've only compressed, for the sake of the example, the text of the book itself, not any of the Project Gutenberg metadata, because there's also, if you download books from Project Gutenberg, there's all sorts of other data in them describing what Project Gutenberg is and where to reach them. I deleted all of that stuff for the sake of this comparison. I'll post the file that I used. So 750 kilobytes. I can't use my 5-bit trick, because if I want to use my 5-bit trick, there have to be at most 32 distinct characters. In the entire book, there are more than 28 distinct characters. It turns out there are 73 of them. So I can't encode it in 5 bits or 6 bits per character. I could try using 7 bits, but we can see sort of the law of diminishing returns. The more characters you have, the less savings you're going to get. And 7 bits versus 8 bits isn't very much savings. I get about 660 kilobytes. Okay, well, I mean, better than nothing, but not great. If I run the entire book through Deflate, it comes out to 280. And if I run it through bzip2, it comes out to 203. So bzip2 actually wins this round. And then LZMA gives me 230. Now, we'll talk about this in a later lecture, but there actually are settings you can give to these compression tools that dictate exactly how they perform compression. I'm running all three on a sort of basic mode because we're not at the point yet where we can talk about those parameters. But typically, for example, running bzip or Deflate or LZMA, you can tell the compressor, I don't mind if you use a lot of CPU time, or it's okay if you use a lot of extra memory, if that achieves better compression. So there are some parameters you can set that allow you to improve compression at the expense of resource consumption. So our goal is to generate, and this is not just our goal in this lecture, but our goal in this entire course is to create a general purpose compression algorithm. I want to write programs that can compress anything, arbitrary binary data. And the problem with that is if I'm compressing arbitrary data, whether or not it's text, but in this case it is not necessarily text, then I shouldn't assume that fewer than 256 possible bit sequences appear. In an arbitrary binary file, especially a large one, I should expect that every possible 8-bit sequence shows up at least once. So this idea that I've been following for the last couple of lectures of reducing the number of bits I used is not universally applicable. That doesn't mean I can't use it. It just means I can't count on it always yielding results. So if I want to design one of these general schemes, I'm allowed to use any clever tricks I want. So I could write a compression program that has a library of different compression tricks it could use. So A, B, C, or D. The problem is, if I design a compression program that has a number of different tricks available, then of course it can choose which tricks it uses every time it compresses an input. So based on the character of the input, it could choose, let's say, technique A and technique C, or technique A followed by technique B. But the problem with that is, whatever choices the compressor makes, it has to somehow communicate to the decompressor. The model we generally talk about, and I'm going to redraw this diagram over and over again in this course and probably in this lecture, the model we generally think of with compression is we've got our original data, which could be anything. We run the data through a compression program. We'll call that C, I guess. And mathematically, we can think of the compression program C as a function that takes a bit sequence and produces another bit sequence. Generally speaking, what comes out of a compressor, we're going to call that in this course a bit stream because it's a bunch of bits. We can't say much more about it than that. It may not even be evenly divisible into bytes, although we usually do set a requirement that if we're going to store it somewhere, that it be byte aligned. So we call this the compressed bit stream. And because the goal of compression is to compact the data as much as possible, the compressed bit stream is often not even recognizable when you compare it to the original data. Later, if I want to recover the original data, I take my compressed bit stream and I feed it into my decompressor. And the decompressor is required, by that basic constraint of lossless compression, to produce the exact same data that I started with. Identical, bit for bit identical. Now the issue is, if the compressor chooses, while it's doing its compression, if it chooses which techniques to use, so if it chooses to use technique A, then C, then B, it has to somehow tell the decompressor what it did. The decompressor has no knowledge about the data besides what you've sent it, what bit stream the compressor has provided. And of course, the bit stream could be stored in a file, it could be sent across a network or whatever, but all that the decompressor gets is that bit stream. So any cleverness the compressor uses has to be somehow communicated to the decompressor. And that creates overhead. And that's our great enemy when we're designing a compression scheme is all the cleverness in the world could be defeated by the amount of overhead I need to communicate what I'm doing to the decompressor. Now, we're finally ready to have some kind of mathematical definition. So in this course, if we think about this sort of conceptual model of how we're doing compression, in this course, I assume that all of the data that we're compressing is a bunch of zeros and ones. So formally, in a mathematical sense, the input data is a sequence of 0 or more bits that are zeros or ones. But really, formally, I could be working with any alphabet I want. So if I want to make a formal definition, so the be-all and end-all formal definition of a compression scheme, I should define it so generally that I'm allowed to switch from binary to ternary or over any arbitrary sequence of symbols that I want. But in this course, frankly, it's always going to be binary. And you know from previous courses that there are lots of reasons that that's an acceptable generalization. If I'm working over any other alphabet, I could just as easily encode that alphabet into binary. So a lossless compression scheme, and remember in this course, if I just say compression scheme, I mean lossless. A lossless compression scheme is a pair of functions, C and D. And both functions take a sequence of bits and produce a sequence of bits of some length. Obviously, we don't assume that the sequence of bits that goes in has the same length as the sequence that comes out, because that would defeat the purpose. And ultimately, to be a compression scheme, the only actual invariant that we require is this property. If I compress a piece of data S and then I decompress it, I should get S back. That's it. So the number one priority for something to be a compression scheme is this lossless property, which is amusing in a certain way because that means that the compression part, the part where I save space, isn't actually our highest priority, because we first have to verify that the data's integrity is being preserved. And there's an obvious reason for that, which is that if I'm allowed to throw data away, then I could reduce everything down to 0 bits. I could write a compressor that just generates nothing ever. So that obviously wouldn't help. Obviously, our first priority is the data must be preserved. And then the second priority, really more of an aspirational goal, ideally, I would like it if the size of what comes out of the compressor is less than the size of what went in. Okay, so C is the compressor, D is the decompressor. This is nice. As somebody with a math background, I really like this. I feel more comfortable now. I see some Greek letters. That's nice. And then I think, hey, if I'm writing theoretical definitions, maybe I could even prove some theorems. Okay, I got one more definition before I try that, and that's this idea of measuring how good my compression is. So we call this the compression ratio. Every now and then I'll call it a compression factor or something similar. It's going to be this. There are different ways to define this. Actually, there are basically 2 different ways, and the question is which thing do I put as the numerator and which thing do I put as the denominator. For consistency with the various books that we're referring to this semester, I'm going to use this definition and only this definition. So if I say compression ratio, I mean this quantity here. And it is just a measurement of the length of the input bit sequence or byte sequence, depending on if we're working in byte-aligned data, and the size of the output of the compressor. So because I've just shown you an equation, I owe you at least one patronizing example. So suppose that I give you an input sequence of 10 bits, and your compressor is able to reduce that down to 5 bits. Well, then our compression ratio is going to be 10 over 5, which equals 2. Which means I was able to cut the data in half. Alternatively, you could think about that 2 as the expansion factor when I decompress. So if I take my compressed data and I decompress it, it will expand by a factor of 2. Okay. Notice that the compression ratio is defined with respect to a particular input. And that's for a reason that we're getting closer and closer to determining, which is that discussing the average compression ratio across all inputs or talking about worst case or anything similar to that doesn't prove to be that productive for data compression. And I'll talk about that in the next couple of slides as I attempt to prove some theoretical results. So once I have all these theoretical definitions, I guess the natural next thing to do is to try and write some magical proof that tells me something like it might be possible to always achieve a compression ratio of at least 2, or always achieve compression of which brings us down to at least 80% of the previous size. So my first question is there a compression scheme, so a pair of compressor and decompressor, over binary strings such that I'm guaranteed that my compressor never does a bad job? So I'll talk about what it means to do a good job in a minute, but at least I would expect, if I want to compress something, I would expect that what comes out of my compressor is no larger than what went in. I guess I'll allow it to be the same size for the time being. We're going to start small, but I'm not going to allow it to be any bigger. Okay, well, turns out the answer to this question is yes, such a scheme exists. It's this one. And this is exactly the kind of shenanigans you expect from somebody with a math background in this context. You're used to this from theory courses. I guess this is a matter of if you ask a stupid question, you get a stupid answer. So is there a compressor that never makes the input bigger? Well, yeah, sure. Just leave the input the same size. So I'll define a compressor that does nothing. And then I'll define a decompressor that also does nothing. Well, I guess that does meet our definition from earlier. It's sort of useless if I care about compression, but it doesn't expand its input. So I guess, in terms of our own schemes, this is our competition at worst. I mean, if our scheme can't compete with a scheme that does nothing, then our scheme is sort of bad. Okay, well, maybe I was asking the wrong question. Okay, so how about this one? Is there a compression scheme that always achieves legitimate compression? None of this keeping the input the same size business. I want to achieve legitimate compression. In other words, the size of the compressed data is always smaller than, strictly smaller than, the size of what went in. And the answer to this question is no. And really, this is sort of liberating because it starts a line of reasoning that results in us understanding that we can't really write some grand unified theorem of compression. And in fact, although we're going to need a lot of theoretical results in this course, we're not going to be able to make much progress with some overarching theoretical attack on the compression problem. We instead have to talk about it in terms of maybe empirical observations or actual data. There are a couple of ways of justifying this. I want to circle around a couple of different properties that this question sort of illuminates. So it's not the case that there is a compression scheme that makes every single input sequence smaller. Now, one way of attacking this is to consider that maybe this is also sort of a badly phrased question. So I guess I shouldn't say stupid question, because there are no stupid questions. Although this is a question where the answer doesn't tell us, it doesn't, it's not that salient. It doesn't give us that much interesting information about the world of compression for a few reasons. So one reason is this. Suppose that, I guess I'll leave this slide up. Suppose that we had a compressor that obeyed this law. Okay, well, if we did, then let's try compressing a 2-bit sequence. So if I compress the sequence 1, 0, well, it has to make it smaller. Okay, so it makes it, I don't know, the single bit 0. Okay, suppose that I compress the sequence 1, 1. Well, it has to make it smaller. So I guess it's going to be the single bit, well, I guess 0 is taken, so it'll be 1. Okay, well, so far this is all right, because if I try and decompress the single bit 0, I'll just get, I guess, 1, 0. If I try to decompress the single bit 1, I'll just get 1, 1. What if I try to compress the sequence 0, 0? What do I get? Well, okay, it has to be 1 bit. Okay, it can't be 2 bits, because then this wouldn't be obeyed. Okay, it's 1 bit. Let's just say it's the bit 1. Well, that's going to be a problem, because then what happens if I try and decompress the bit 1? Am I going to get this, or am I going to get that? And you can maybe see the problem here. So if it always compresses, then I'm going to run out of bandwidth very quickly if I try to compress 2-bit sequences or 1-bit sequences. I mean, frankly, what if I try and compress the single bit 0? I guess I get 0 bits, the empty string. Okay, fair enough. What if I try and compress the single bit 1, also the empty string? Well, that's going to be a problem. And even worse, what if I try and compress the same thing over and over again? So I take some sequence S and I compress it. So we'll say, all right, we've got a sequence S and its size is n. And then the compressed sequence has to have size, at most, n minus 1. And then if I try compressing that, so if I run it through the compressor again, it has to have size at most n minus 2. And hopefully this also illuminates a fallacy with this reasoning, which is if this question had the answer yes, then I would be able to compress literally anything into 0 bits, which makes absolutely no sense. Because how would I decompress that? I'm just taking every piece of information in the entire universe and reducing it down to nothing. If this were true, then nothing that we currently understand about information or computation or mathematics would make any sense at all. We wouldn't need computers to have hard drives or memory, frankly. A CPU could have one register and store all of the data ever to have existed in the universe. I'd like that if that were the case. I don't think that that's the case, and I think I can prove that that's not the case. So as far as a formal proof goes, we could write a proof by contradiction that basically leverages some of these observations. We could also write a combinatorial proof, which I'll just show off quickly. I won't write it from scratch, but I can show off the basic idea behind the combinatorial proof, and it uses the pigeonhole principle. So let's choose some bit sequence length. So I want to consider all of the inputs of a particular length. So we'll consider all bit sequences S that are elements of, that are n element bit sequences. Okay, well, how many of those are there? So these sequences have size exactly n. Well, there are going to be 2 to the n of them. What I'm going to do is illustrate that if I feed all of those different bit sequences into my compressor, and what comes out always has to be smaller, well, then obviously everything that comes out, so the compressed size, has to be less than or equal to n minus 1. And what I'm going to do is leverage the same observation I made a couple slides ago with this stuff, which is if I try to compress all of the different 2-bit sequences, so 0, 0, 1, 0, and 1, 1, there aren't very many 1-bit sequences that I could be compressing them into. And that applies generally. In general, if I take every possible n-bit sequence, so all 2 to the n of them, and I run all of them through the compressor, and I consider the image of what comes out, so that would be this. So I consider the set S of all 2 to the n things, and then I try compressing every single one of them and look at the set of what comes out. Well, obviously, if I'm going to be able to decompress it, this set, we'll call it SC, has to have the same size as S, so that I have some way of going backwards. So every input bit sequence has one unique output bit sequence when I run it through the compressor. So that means that for lossless compression to hold, this has to hold as well. But I'm going to be able to show that if every single sequence in SC has to have length at most n-1, well, how many possibilities are there? Well, here are here how many sequences there are of length 0, here how many sequences there are of length 1, and so on up to length n-1. If I sum those up, the total number is actually equal to this. You might be familiar with this numerical identity from some previous algorithms course, but it still holds, and that means that there aren't enough bit sequences available. There are 2 to the n bit sequences that I want to compress, and only 2 to the n all minus 1 that are smaller. So there's no way for me to compress all of them in such a way that I can decompress them. So that's too small, and that means that there has to exist at least one bit sequence that comes out to be the same size or bigger. Now, it's actually a lot worse than this, because this proof is just saying if I try to encode only things of length n, only these 2 to the n strings, then at least one of them has to come out to be the same size or bigger. It's not considering the fact that I also might want to compress strings of length n-1 or n-2. What happens to those? I've already eaten up almost every string of length n-1 or less just compressing these 2 to the n strings. So what happens if I try to compress strings of a shorter length? It gets much worse. So generally, though, what we have here is now this understanding that it is impossible to expect that our compressor will always shrink its input. Now, we could use that and say, well, maybe that means some inputs remain the same size. But unfortunately, it gets even worse. It turns out that compression is basically a zero-sum game. So we could elaborate on this proof. We could actually write a formal proof of this fact, but I'm not going to do that. We could prove that if a compression scheme ever achieves compression, so if any input gets smaller, there must be inputs that get bigger. So in other words, every time I make an input smaller, I am displacing something and making some other input bigger. I can justify that in a broad sense. So if we again let's consider a case where our compression function does make something smaller. So suppose I take the 3-bit string 110 and my compressor, so here's the action of the compressor here, my compressor manages to turn that into the 2-bit string 01. Now let's consider all of the other inputs that are smaller than 3 bits. So every possible compressor input that's smaller than 3 bits. Well, what do we have? I guess there's a 0-bit input, which is a little bit creepy to think about compressing a 0-bit string, but yes, that does still count. There are these 2 1-bit inputs, and there are 4 2-bit inputs. Okay, so what does the compressor do to these? Well, let's just make something up. Let's try and design our compressor, I guess, just piecewise. So the empty string, okay, that's creepy, so I'll just have the empty string go to the empty string. Okay, it's not getting any smaller. Our proof a couple of minutes ago showed that we can't expect every string to get smaller, but maybe some strings just stay the same size. Okay, 0, what does that have? Well, let's say that goes to 1, just to shake things up. And then 1 goes to 0. Okay, so 0, 0. Well, let's say that goes to 1, 1. 0, 1. Well, let's say that goes to 0, 0. Okay, fair enough. 1, 0. Okay, so 1, 0 is going to go back to itself. Well, that's allowed. It's weird, but it's allowed. And then what happens here? There's nothing left. There are no 2-bit sequences that I can use for this. And there are no 1-bit sequences that I can use for this. And there are no 0-bit sequences. So what do? I have to make up something, so I guess I'll have to give it a 3-bit sequence. So we'll say 1, 1 goes to 0, 1, 1. Okay, too bad. So what I hope you can see from this illustration, though, is that every time I get an input that gets smaller, so here I've got a 3-bit thing that ends up in the realm of 2-bit things. What I've basically done, though, is I've just bumped up one of the 2-bit things to have an image that's 3 bits or larger. Or I've done some I've created a cascading effect where something gets bumped out. There are only a certain number of bit strings that are smaller than 3 bits. And if all of them are going to be compressed or stay the same size, there's no room for a 3-bit thing to achieve compression. So what I end up with is this property that compression is basically a zero-sum game. So anytime I achieve compression, there must be some other input that ends up expanding, basically. And so, in a sense, though, I would argue that that's sort of liberating because that means that we're not going to get anywhere if we try and write some long proof about whether a scheme achieves compression on average, because it's sort of a zero-sum game. If I get compression on one input, I lose compression on another. Instead, we should pivot and instead think about writing compression schemes that do a good job on inputs that we're likely to actually see. Some inputs get smaller, some inputs get bigger. Let's just design a scheme that makes the input smaller if it's the kind of thing that we tend to actually see. So if we consider all possible bit sequences of a certain size, and for the sake of being dramatic, let's consider all possible sequences of 1 billion bits. So on the order of about a gigabit of data. Well, that would be, how many bit sequences are there? Well, 2 to the power of 1 billion, 2 to the 10 to the 9. So all the sequences of 1 billion bits, again, approximately a gigabit of data. So about 125 megabytes of data. This is an obscene number of bit sequences. And if you don't believe me, go try and generate them. And then you can drop by the office hours when you're done generating them, and we can talk about it. This set of bit sequence is so massive that if we consider all of the possible sequences of length 10 to the 9 that have ever existed, and I'll define existed to mean they've ever been part of a computer's memory or part of any other persistent storage anywhere in the universe at any time, or they've been stored or transmitted over a network in some ephemeral manner, so not necessarily stored, but transmitted. All of the sequences of 1 billion bits that have ever been in existence at any time in the existence of the universe probably still, like in the context of computing, probably still is only a tiny fraction of the total. So if we consider every sequence of 1 billion bits that's existed on someone's hard drive or been transmitted on a network channel or something, it's tiny compared to the total number of bit sequences. So that means that if we consider actual data, even by the most liberal definition possible, where actual data is literally anything that's ever existed, so any data that's ever existed anywhere for any reason for any amount of time, that's still only a tiny fraction. So why don't I just write a compression scheme that's really good at making this kind of thing smaller, and if it has to make something bigger, have it be something from out here. Something from out here in this hinterland full of, I don't know, what's the opposite of actual data? Well, actual data is stuff like this video, or these slides, or the text of A Tale of Two Cities, or I don't know, even a bunch of random numbers that I generate if I store it on my hard drive. I'm willing to call that actual data. What's the opposite of actual data? I'm going to use the term in this course, I'll just call it random noise. So static, essentially. There's lots of random noise out there in the universe, I guess. Good luck generating all that randomness, but there's lots of sequences of bits that nobody's ever used for anything. And if my compressor makes those sequences bigger, who cares? Because nobody's ever used them for anything. What are the odds that my compressor ever gets an input from this collection of random noise? So that's the problem that we're now trying to solve. If we know that compression is a zero-sum game, but we also know that the set of inputs we're ever likely to compress in the entire history of computing is tiny compared to the set of random bits of data that are random noise out there, I'll just write a compressor that's good at compressing this stuff. And so from here on forward, that is how we're going to approach this. And although it's a bit wrong to say that compression is all about the study of patterns in data, it's certainly true that patterns in data help us a lot when we're doing compression. And it's also true that in actual data that we are likely to see in everyday use, there are tons of patterns. That's all great. That was all fun. It's nice and philosophical. We're all thinking about the universe now, but how do we compress this data? Come on, it's 416 characters. It's English text. It's from a book that's now 170 years old or something. We've got to have something we can do to this. So it's 416 characters. Can we make it smaller than 416 bytes? Well, yeah, of course. Of course we can. We saw that earlier. Deflate can do it, so can we. But on the other hand, we still have to answer questions about how we're measuring this. So suppose that I'm able to reduce this text to a 10-byte representation. I can send you a 10-byte file. And like here's my file here. It's my 10 bytes. And I send you this 10-byte sequence. I can just write it down on paper. It's 10 bytes long. And I say, if you take this 10-byte sequence and you feed it into my special proprietary decompression program, you will get back the original text. So I guess we'll call this text, and it's this stuff. Great. But I should add that my compression program is 1 megabyte in size. So, I'm going to give you my special decompression program, and you're going to feed in this 10-byte sequence and get back the original text. Am I playing fairly to say that I have compressed the text to be 10 bytes in size? And I would argue that the answer is actually no. And I can give you the reason why in a pretty simple flippant statement, which is, why does it have to be 10 bytes in size? I could make it 1 bit in size. So here's my compression tool. I feed in the text, and it goes into my compression tool, and the compression tool looks at the text and says, is it this sequence of text? Is it the beginning of Tale of Two Cities? If so, it generates the single bit 1. Okay, my decompression tool is a C program that contains one if statement. And the if statement is, if you gave me the bit 1, just print out this entire sequence of text. In other words, I could hard code this entire sequence of text into the decompressor and then send you the decompressor and say, oh, look at my 1-bit compression. But no, that's cheating because because the decompressor works on such a small number of inputs, that is to say, this one input, I'm allowed to hard code the input into the decompressor, and then really what's happening is all of that 416 characters, they're just hiding inside the decompressor. I've played a shell game. I've used some accounting tricks to make it look like I'm achieving compression when I'm not. And that brings us to clarification 2, which is, yeah, to what extent does our scheme have to be general? If I'm allowed to compress just this one input, then I have all sorts of tricks I can use to hide data in the decompression executable as opposed to actually sending it to you. But if I talk about the scheme being general, so if I say, oh, it's not sufficient for it to only compress this piece of text, is it sufficient for it to compress just text? Would that be cheating? Would it be cheating to write a compression tool that only works on English text or only text in general? What about images? We do have compression schemes just for images. So at what point am I cheating? A third clarification, which is in a different realm, I guess, is this practical consideration of what if I send you my 10-byte encoding and a decompressor that isn't cheating, but the decompressor apparently takes 1,000 years, or it takes so much memory that you can't run it. Well, how would you know whether it works? How do you know whether compression is achieved if you can't verify that the decompressor produces output that matches the original input? So for practical reasons, we do sort of require that for verifiability, if nothing else, for scientific rigor, we need you to be able to run the decompressor and run the compressor in a reasonable amount of time. So and this is one that's a bit difficult to define in a concrete way because resource constraints are always relative. The amount of resources that I have to use on a computational problem when I'm out standing at a bus stop using my phone versus the amount of resources that I have if I'm logged into a supercomputer cluster is obviously different. And depending on the context in which I'm working, 100 terabytes of memory might not be that bad. I would argue that in this course it is almost always that bad. But resource constraints are something that are a bit relative, so we're going to define them pretty pragmatically in the context of this course. Before we can actually design a compression scheme, we do need to figure out answers to those questions. So the first two issues are essentially two stages of the same question, as I pointed out, which is at what level of generality is sufficient for us not to have to consider the size of the decompressor, for example, when we consider whether compression has been achieved. So my argument is this. First, it turns out that there actually are a lot of useful reasons why you might want to write a compression program whose job it is to compress literally just one input. And there are compression challenges out there, contests that you can enter, that involve compressing one piece of data. A famous one is, here is a 1 gigabyte file that has been derived from Wikipedia data. So it's primarily sort of English text and markup, so metadata. If you can take this 1 gigabyte file and compress it to be smaller than the last person, so other people have previously attempted to go for this prize. If you can make this 1 gigabyte file smaller than the previous record, you win $1,000. However, we count the size that you achieve as being both the size of the compressed data and the size of the decompression tool, because obviously you could be hiding data in the decompression tool. I would argue that makes perfect sense when you're compressing literally just one thing. As far as generality goes, I would argue that we can set a pretty sensible boundary where we no longer have to measure the size of the decompressor to be allowed to measure compression. So we can just measure what comes out of the compressor as the compressed representation. And so if we develop a fully general scheme that compresses literal, arbitrary binary data, and I send you a decompressor that's 1 megabyte, but the decompressor can decompress literally anything that I compress. I can compress any data I want, 5 megabytes of data, 5 gigabytes of data, whatever, then it doesn't make much difference that decompressor is 1 megabyte. If I am decompressing a 5 megabyte bit stream or a 5 gigabyte bit stream, that 1 megabyte doesn't make much of a difference. In a sense, it gets sort of asymptotically overwhelmed by the things that I can be decompressing. More generally, I think, we can define a scheme as being sufficiently general as long as the number of possible inputs is infinite. So if I'm compressing, for example, English text, well, there are an infinite number of English text files, and they can be of any size. So I can have a 416-byte text file. I can have a 400 million byte text file. That's fine. And so as long as the set of possible inputs, the domain of the compression scheme is infinite, then I don't mind that much that the decompressor takes up 1 megabyte, because that's a constant. Once I compile the decompressor, it can decompress anything forever. And therefore, that 1 megabyte isn't too bad. If I'm only going to compress or decompress one thing, then oh yes, definitely I want to count that 1 megabyte. In this course, because we are going to be working in domains that are infinite, so all sets of English text or all possible images of any size, then it's reasonable that we don't care how big the decompressor is, because we compile the decompressor once and we can use it over and over again. As far as the performance angle, what I'm going to do in this course, because I don't want to set an arbitrary limits, like, you can use 1 gigabyte of memory and no more, not 1 byte more. What I'm going to do is set reasonable limits for the pragmatic constraints of a course. So this is a university course, which means it's 3 months and a bit long. I have to mark everybody's assignment, and everybody in this context is somewhere between 50 and 100 people, and they're all handing in assignments. I want to test them all on multiple inputs, and I want to have all the testing done in a few hours. And so I need it to be able to run on a computer that I actually have, which these days computers we could expect have somewhere between, on the lower end, about 4 gigabytes of main memory up to maybe 64 gigabytes, with the sort of average these days probably falling somewhere between 8 and 32. It's reasonable, therefore, to expect that the compression schemes that we work with use an amount of memory that's in that ballpark, but generally trending towards the low end, so less than 4 gigabytes, probably less than 1 gigabyte for small inputs. If I'm trying to compress a file that's 100 kilobytes in size, it's probably reasonable to expect that I shouldn't need a gigabyte of memory to do that. And we will talk about this on a case-by-case basis, so for assignments you will be given more specific requirements. Because in this course we all have a common reference platform, so a server we can all log into to run our code, we'll just use that. We'll say it has to run on this machine. If it doesn't, I don't care why, memory or CPU or whatever, if it doesn't run on this machine in a certain amount of time, so let's say, 15 seconds for an input that's 5 kilobytes or 100 kilobytes in size, then we have a problem. So I will follow the pragmatic ideal that basically in this course all we care about for resources is it must be able to run in a reasonable amount of time on the hardware that we have, such that it can serve our purposes in this course. In general, as far as time, we want, ideally, when we implement assignments and things, and you will receive some marks for this on some assignments, we want our tools to be competitive, and that's a bit of a weasel word, competitive with the big three. So deflate, we'll realize deflate in this course via gzip. So gzip, bzip2, and LZMA. I want our programs that we write to be competitive with those. Now, not necessarily in terms of compression. So it might be very difficult to get the same compression as the LZMA executable because obviously it's been written over many years by many different people, whereas we only have a few weeks or months to do it. It's also unreasonable to expect that your code can compress a 10 megabyte file in exactly the same amount of time as LZMA, again, because over many years, with many different sets of eyes, the LZMA executable has been developed by both compression experts and optimization and architecture experts, so it's probably pretty fast. On the other hand, it is reasonable to expect that your compression tools be in the same ballpark. That is to say, if LZMA or gzip take about 10 seconds and yours takes about 20 seconds, well, fair enough, that's going to happen. If yours takes 5 years on inputs where they take 10 seconds, then we have a problem. And if yours takes 5 hours, we still have a pretty significant problem. As long as it's in the same ballpark, so on the same order as those executables, then we're looking good. And the slides agree with what I just said about the speed thing. So we have enough information now, I guess, to state some restrictions that allow us to develop a legitimate compression scheme for that snippet of text. It only took us an hour and 10 minutes to get to this point. I want to design a scheme with the following properties. The first rule is all data, so my uncompressed data and my compressed data, will be stored as a sequence of bytes. That's a pragmatic constraint. That is just because I'm going to be writing a computer program to do this using data stored on disk in a byte addressable environment. So I have to work with bytes. When I make, and it makes sense that our uncompressed data is a bunch of bytes, but our compressed data has to be too because I want to store it to disk. All this is really saying is, if I generate a bit stream that doesn't uniformly break up into bytes, so for example, here's a bit stream. This bit stream is 10 bits long. If I generate a bit stream that isn't evenly divisible into bytes, I just have to pad it out to be divisible into bytes. So I could just add 6 more bits to make it divisible into bytes. So at worst, that's going to add 7 extra bits of overhead to my encoding. Not a big deal. 7 is a constant. As far as the other rules, those are based on what we've just seen. So first, I would like a general scheme. I would like a scheme that can compress, in this case, literally any sequence of bytes. So not just text, and not just English text, but literally any sequence of bytes. To be clear, it would be reasonable to restrict my input to only want to compress text or English text, because there is an infinite amount of English text out there. So I'm not making my input domain so specific that it's no longer infinite. In this case, though, I want to be able to compress any sequence of bytes. Now, as far as our earlier idea of a range reduction or a bit reduction, so using less than 8 bits per character, rule number 2 does make a little bit of a mess for us, because it means that we can't always assume that the data that comes in can be stored in less than 8 bits per symbol. That isn't inherently wrong, though. There's nothing wrong with that except for the fact that that means that there are going to be some inputs that use more than 128 distinct characters that aren't going to be able to achieve very good compression if we just use our bit reduction technique. As far as our rule number 3 is concerned, we also have that requirement, as I wrote earlier, this diagram I keep using. Everything that the compressor does has to somehow be communicated to the decompressor, and it does that via the bit stream. So I have this compressed bit stream in the middle here. And the compressor produces the bit stream, and the decompressor takes the bit stream and produces the original data. If the compressor does anything, if it makes any decisions while it generates the bit stream, the decompressor needs to have some way of learning those decisions. And that usually means I have to somehow encode them into the bit stream. There are a few ways to do this. With really ingenious schemes, like the one we're going to see in the next lecture, there's a way of doing this without really adding too much to the bit stream. What we're going to see later in this lecture, though, is one easy way of communicating your decisions to the decompressor is to just add extra bits to the bit stream containing evidence of those decisions, to add overhead. The problem is, the more overhead you add, even if the amount of overhead you add is constant, like 100 extra bytes or something, the more overhead you add, the worse the compression ratio is going to get on small inputs. If the input is small, then likely the compressed version of the input is also small, and that overhead takes up an outsized chunk of the bit stream. So I want the overhead in my scheme I'm about to develop to be as low as possible on short inputs. Overhead isn't bad, but this is a scheme where I want to optimize the overhead to be small for short inputs. And I should add, of course, as I said, overhead isn't bad. Adding some extra data to my bit stream can really improve things. So we saw earlier, for example, that the deflate scheme got better compression than LZMA on our short sequence of text. One of the reasons for that is because LZMA has more overhead. And that leads LZMA to have great advantages on large inputs, but puts it at a disadvantage on short inputs. So what we're saying here ultimately is, for this particular application, I don't want to compromise the compression ratio of small inputs just because I can get better compression on larger ones. I want it to ramp up sort of evenly. I want inputs of all sizes to get decent compression, as opposed to short inputs getting bad compression and long inputs getting good compression. There's also this streaming requirement. We're going to spend a lot of time fighting with this streaming requirement during this course. And so I'll just redraw that diagram again. The streaming requirement is, you can interpret it in a few different ways, and I'm not sure which ones are intuitive at this point in the course, but the way I'd like to present it is the streaming requirement is this idea that the compressor can generate bits of encoded data pretty quickly once you start providing your input. Suppose that the input were 5 gigabytes long, and the compressor reads through the input from start to finish. I would like it to be the case that the compressor can begin generating output before it's reached the end of the input. So that's one way of viewing the streaming requirement. And if we take that to an extreme, consider if I'm compressing continuously for a huge period of time. So consider that there are streams of streaming video out there that have been continuously streaming for years. And for example, if you've ever maintained like a security camera system and it uses digital video, you can tune into it whenever you want. The compressor is operating continuously. It just keeps generating compressed data. It doesn't have to know all of the data before it generates the compressed representation, because that would be impossible. The idea behind the streaming requirement is the compressor is allowed to save up little bits of the data, but it is not allowed to save up all of the data. So the compressor has to be able to compress data without seeing the entire input sequence at once. And we can also frame that in terms of using constant extra space. So it's valid for the compressor, for example, to say, I'm going to begin compressing, I'm going to save up 500 bytes of input, or 500 kilobytes of input, or 5 megabytes of input, and use and analyze those 5 megabytes and then compress them. But it's invalid for the compressor to say, I'm going to wait until I have all of the input, and then look at all of the input, analyze it for patterns, and then output my compressed representation. And there are lots of reasons we want this requirement. So one of them, I guess, could be that we could think of literal streaming. So we could say, I'm compressing some data as I receive it. So it's network data, and I'm receiving it from one network source, compressing it and sending it back out again. And I have no idea how long it is, and I can't seek through the stream. So if I'm receiving data in a stream, I obviously can't rewind it. I can't read it more than once like I would a file. And therefore, I have to find some way of encoding it before more data comes in. I can't save it up because it's going to keep coming. But basically the way we interpret this is we'll have to assume that you can use a constant amount of memory. You are allowed to save up chunks of input, but they have to be constant sized chunks of input. You are not allowed to read your input twice. So for example, on our assignments, we assume that input comes in through standard input as a stream of bits, not as a file on disk. So you're not allowed to open the file, read it, close it, open it again, then read it again. You're not allowed to do that. You have to interpret your data as a continuous stream of data, and you aren't allowed to save up all of it. Because obviously if you saved up all of it, you'd eventually run out of memory if it was a huge amount of data. And as I said, I can't emphasize this enough. You are allowed to store some chunk of your input data, just not all of it. It has to be a constant sized chunk. You can make data structures, you can cache the data, but it has to be in chunks that are of constant size, so bounded above by some constant. All of our big three schemes do that. So gzip, bzip, and LZMA all do store some subset of the input data, but they don't store all of it. And the workaround the slides are referring to is essentially what I just mentioned. We're not going to use that workaround today. We will use it a lot later. So other than the rules we've just given here, we also ideally want to get good compression. And if we can manage it, consume as few resources as possible. Now, often you'll notice, and we'll see why really quickly in this course, I'll just draw the diagram again. Because the process of compression is usually a lot harder than decompression, because the compressor has to make choices about what to do, whereas the decompressor just follows instructions given to it in the bit stream. And because of that, compression is a bit harder and generally takes longer. There is usually asymmetry between compressors and decompressors. If you have such asymmetry, or if you're designing a scheme and know that there's going to be asymmetry, it's a good idea to prioritize having the decompressor be fast and use as little memory as possible. Not only because that's going to happen anyway, because compression is harder, but also because often when you compress something, you might decompress it more than once. So I might compress an archive file and then send it to a bunch of people, distribute it across the internet or something. So a lot of different people might be decompressing one single compressed representation. And therefore it's a good idea that the decompressor be faster and use less memory, because you might be using the decompressor on average more often than the compressor. that's a constraint. That's not really a constraint, I guess. That's something we'll keep in the back of our heads for this semester. And in general, you'll discover your decompressors probably are faster than your compressors. Our first few assignments are just writing compressors, though, so we won't worry about decompression that much early on in the course, or implementation of decompression. Now, at some point in this lecture, we actually have to do some compression. So before we can do that, let's shorten down, for the sake of demonstrating our technique, let's shorten down our excerpt just to the very first bit. So it was the best of times, it was the worst of times. This has length 51. If we're storing it in 8 bits per character, that's 408 bits in total. There are 15 distinct characters in this excerpt. So in this case, I could use 4 bits. If I really want to exploit that bit reduction trick that I've been trying to do for the last couple of lectures, I could use 4 bits per character, because obviously 2 to the 4 is equal to 16, and I have 15 distinct characters. I could come up with a way of encoding these 15 characters into 4 bits apiece. And then the question is, oh, well, if they were previously stored in 8 bits and I can get them into 4 bits, does that mean I can get a compression ratio of 2? Can I cut my space consumption in half? And the answer, it turns out, is no. And the reason is overhead. It's that problem of having to tell the decompressor what you're doing. So I'm not allowed to require that all of my inputs have only those 15 characters. That would be cheating. I have to accept any sequence of bytes. So that means if I choose to store this particular input in 4 bits per character, I have to have some way of telling the decompressor, oh, I'm going to use 4 bits. And I'm going to have 15 different characters. And also, here are the 15 characters I'm going to use. The decompressor has to know all of that stuff, because if my scheme is general, how else would it know how I'm encoding my data? I am allowed to use fewer than 8 bits per character, as long as I have some way of telling the decompressor what I'm up to. So here's a scheme that does that. Here is a complete compression scheme. And the bit stream contains the following things. So I take my input string S, and then I construct a compressed bit stream containing all of the following data. The decompressor, if I'm going to use fewer than 8 bits per character, the decompressor has to know how many bits I'm using. The way I'm going to tell it how many bits to use is I will store into my bit stream the number of distinct characters that occur. So if the number is 15, then both me, the compressor, and the decompressor know that I'll use 4 bits. If the number is 28, I guess I'll use 5 bits. If the number is 71 or 73, then I'm going to use 7 bits. So if I tell the decompressor how many characters I have, it'll be able to work out how many bits I need to use. So I'm going to store that number. So how many possible characters could occur? Well, there could be 1 possible character, there could be 15, there could be 28, but there could be as many as 256. So I have to tell the decompressor how many distinct characters occur. And if I want to represent the number 256, I have to use 9 bits, which is sort of weird. I can't use 8 bits because the largest 8-bit value is 255. Now, connoisseurs will look at this and observe with some clever arithmetic, they could find a way of storing this number in only 8 bits by leveraging something else they might know about the data stream. I'm not going to do that. I'm going to play this straight up. If I want to represent the number 256, I need 9 bits. So the beginning of my bit stream will be a 9-bit value, which is a number between 0 and 256 that tells the decompressor how many distinct characters occur. Now the next thing is, which characters are those? If there are 15 distinct characters, which characters occur? The decompressor has to know that. So the next thing in my bit stream is a list of all the characters that occur. I'm going to exploit a trick here to avoid having to represent too much extra data. So suppose only 4 characters occur. So there are these 4 characters. And I decide to give these arbitrary bit encodings. So A becomes 1, 1, S becomes 0, 0, D becomes 0, 1, and F, actually I'm going to choose for S to become 1, 0, and F to become 0, 0. So if I do this, one way of conveying that I'm using this encoding to the decompressor is to just tell in my bit stream to say, well, the character A is going to be 1, 1, so I have to represent A in 8 bits. I actually have to provide the 8-bit encoding of this to give the mapping to the decompressor. And then S is going to be 1, 0, but that's a little bit wasteful. I have a trick I can use, which is if I'm using 2 bits for each character, does it really matter which 2-bit sequence each character gets? I would argue it doesn't. Who cares? If they're all 2 bits long, it's all the same to me. So what I'll do is just choose the sequence cleverly in a way that the decompressor can figure out what I mean. What I'll do is tell the decompressor I've got 4 characters. They're going to be A, S, D, and F. I'll actually provide them in whatever order I want. If I provided them in a different order, if I always provided them in alphabetical order or something, I could probably save some space, but I won't even bother with that. If I tell the decompressor there are 4 characters, here they are, then maybe the decompressor and I can both come to an agreement that if you want to know the 2-bit encoding of each of the 4 characters, just go in order with binary numbers. So A becomes 00, S becomes 01, D becomes 10, and F becomes 11. That's it. So I don't actually have to tell the decompressor which encodings I'm using. It's implicit in the order that I provide them. And that's what's happening here. I provide a list of all n distinct characters, and it's assumed that the first element of the list becomes 0. So its bit encoding will be all zeros. The second becomes 1. So 0, 0, 0, 0, 0, whatever, 1. And then finally, after that, I actually provide the encoding of the message. So my input data now gets encoded into as few bits as I'm able to use. So this is, if I consider the number of distinct characters to be n, the number of bits that I need to represent all characters is the ceiling of log base 2 of n. So if I have 15 distinct characters, this would work out to be 4 bits. So then I actually provide the stream of bit encodings of each character. And finally, to obey my rule number 1 from earlier, I add a few extra 0 bits to make sure that I have that what I end up with breaks into an even number of bytes. A whole number of bytes. All right, so if I take my 51 character excerpt of my original text, there are 15 distinct characters, so n equals 15. And here is my list of characters. Okay, so to provide this to the decompressor, I have to, so for steps number 1 and 2 of my scheme, I have to first, before I output even the first character of my message, I have to tell the decompressor what character set I'm working with. And that means I've got my 9-bit value for the number of characters, 15, followed by a list of the 8-bit encodings of each of the different characters I'm going to use. So space, then comma, then uppercase I, then A, then B, and so on. And when I'm done with this, I've already used 129 bits. So I have 51 bytes in my input. I'm already up to 17 before I've stored the first actual character of my message into the compressed bit stream. All I was doing up until this point is just the overhead, just telling the decompressor what I'm up to. When I've done that, so here's where the overhead ends. So this part I'm highlighting here, this is the overhead. Everything afterwards is the actual message followed by a little bit of padding. So everything starting here is the message, and then at the very end, these last 3 zeros are padding to make sure that what I end up with can be evenly divided into bytes. So that's it. That's the result of applying all 4 steps. That is the complete compressed bit stream of my 51-byte message, and it's 42 bytes long. So even though I said I have a bunch of characters being stored in 8 bits, I could store them in 4 bits. Doesn't that mean I can cut the space in half? Well, no, because the amount of bits you need to explain what you're doing might negate the advantage that you're looking for. And in this case, I get a compression ratio of 1.2. So I've managed to achieve 20% or so. That is not the 2 times improvement that I was expecting. And that's one of the reasons why this idea we've been trying, which is this bit reduction, is a little bit too good to be true. We still have to tell the decompressor what we're up to. Now, if I try the same scheme on my original text, finally, it's been an hour and a half, and I finally have found a way of compressing this 416-byte segment. I end up needing 290 bytes. So I use 5 bits per character, and I tell the decompressor which characters I want, and I end up with a compression ratio of 1.4. Now, although this isn't the improvement that we were really hoping for, it is still pretty good. So in an hour and a half, knowing very little about compression, I'm still able to achieve an improvement, a compression ratio of 1.4, so 40% or so. That's pretty good. And if I could go further, using the techniques we learn in the next few lectures, I probably could improve on that a lot. I've already made pretty good progress of achieving compression, even though in the meantime I've learned that compression isn't always possible. Sometimes your compressor will expand its input. So the fact that I've managed any compression is actually still some kind of achievement. Now, we know that the compressor will always expand its input. If there are inputs that shrink, there will be inputs that expand. So it shouldn't surprise you that a very common question and a very common exam question in this course is, here is a description of a compression scheme, or design a compression scheme with these parameters, and then tell me an example of an input, or classify the types of inputs that will expand. So here's an input for the scheme we just designed that expands. It is 3 characters long, and each character appears only once. So it's 3 characters with 3 distinct characters. And maybe we already know intuitively, as the number of distinct characters goes up, the compression ratio tends to go down a little bit. So the more distinct characters you have, the more overhead you're going to have. So this case where I've got as many distinct characters as possible is sort of a natural option if I'm considering bad inputs that are going to result in bad compression. So also worth considering is, in the overhead that I have to produce, I have to provide the 8-bit encoding of all 3 of the characters of the input. If I just store the input in 8 bits per character, that's 24 bits. If I encode it using my compression scheme, I need 24 bits as part of my overhead. So the original message is actually a subset of the overhead, sort of strangely. So we sort of know already we're out of luck as far as getting compression here. So I store my 9-bit value number of characters, that's so the number 3. Then I give the list of characters, and then I encode each character in 2 bits. But I mean, some good that's going to do me because I'm already over the limit, and then I have this extra 0 for padding. So the compression ratio now is 3/5, which is 0.8. So it's less than 1, which means I'm getting expansion, which is no good. But on the other hand, I shouldn't feel too bad about that, because any compression scheme that achieves compression will occasionally have expansions happen. The question here, I've already made a lot of progress. This is supposed to be an exercise. You can think about this. What I just said makes a great deal of progress towards this characterization. So the question here is, does the scheme that we've just developed, it is a complete scheme. So it went from my general idea of bit reduction to a concrete set of steps I can follow to compress and decompress. And it would be possible now to go write a C program that reads data, produces this bit stream and saves it in a file, and a second program that reads the file with the compressed bit stream and decompresses it. You might even want to try doing that. It won't take very long, and it would be a nice way to get back into writing that low-level C code that you're going to need in this course if it's been a while since the last time you wrote C, because you're going to need to write a lot of C code, and I don't want it to be too much of a surprise when those big assignments come around. The question is, does the scheme we've just developed, does it actually meet our criteria? Well, okay, rule number 1 obviously is satisfied. So we took extra care to make sure that the output of the compressor was stored in, byte aligned. So it's a whole number of bytes. So that's fine. But rule number 1 isn't the hardest one to satisfy. Can the input be any sequence of bytes? Well, the answer is yes. So the scheme is designed for cases where the input contains a small number of possible characters, but it's able to work on any sequence of bytes. So rule number 2 is satisfied, even though we know there's a performance issue if the number of distinct characters is greater than or equal to 128, because at that point, the message has to be sent over in 8 bits per character. On the other hand, and sort of stemming from the same issue, if I think about a short input, let's consider maybe 50 characters. If all 50 characters are distinct, that'll be an input that expands. Because if all 50 characters are distinct, I'll have to send over 51 bytes plus 1 bit of overhead in addition to all of the actual data, which again at this point will be expanding because I'll have sent the entire message in the overhead, as we saw a few slides ago, as we saw in this example. So actually, rule number 3, we're really not satisfying rule number 3 here. If we have these inputs with large numbers of distinct characters, we run the very real risk of not achieving compression because the overhead will keep expanding. So our scheme actually doesn't satisfy rule number 3. And even worse, it definitely doesn't satisfy rule number 4, because rule number 4 says no matter how long the data is, so no matter how many gigabytes of data I give you, you are able to encode and decode that without having to store all of the data, with using only a constant amount of extra space. But if the data is encoded in a streaming fashion, so if the compressor receives the data as a stream, the compressor has to store all of the data if it wants to determine how many distinct characters there are. To know how many distinct characters there are, the compressor has to see the entire input. If the input is a stream, the compressor has to store the entire input, or else it's going to lose it, because it can't go back and read it again. And that means that rule number 4 is just not satisfied. So we developed a real compression scheme, and it does achieve compression, but it's not even able to satisfy the constraints that we wrote for it during this lecture. So one question to think about later is, can we fix the scheme? And it turns out we actually basically can. There's always going to be overhead if we make variations to this scheme. So we still want to preserve the idea of doing this bit reduction. So obviously, if I'm asking you to modify the scheme and you just recreate it from scratch using some other technique, you could get better results. But keeping the idea of using fewer than 8 bits per character when that is feasible, is it possible with some small modifications, so tweaking the scheme that we gave earlier in the slides, to have it satisfy at least rule number 3? Now, whether we can satisfy rule number 4 is a different question. That's a bit of a tough one. There are tricks we could use, but it's a bit of a tough one. But we could satisfy rule number 3, and the exercise I'm giving you here is see if you can modify the scheme to otherwise do everything else the same way, but encode the overhead a little bit differently, such that the overhead is never, under any circumstances, more than 32 bytes. Maybe it's always going to be 32 bytes, but never more than 32 bytes. And if you do that, then of course there will still be cases where the input expands, including the input ABC that we saw earlier. But on the other hand, if we can constrain it to 32 bytes, that's way better than the overhead would be in a lot of cases we should be able to foresee. So if the character has 50 bytes, if the message has 50 characters and all of those characters are distinct, then you would need at least 50 bytes of overhead. If the message has 150 characters and all of them are distinct, in the scheme we already developed, we would need 150 bytes of overhead. The exercise is to see if you can find a way to limit the overhead to 32 bytes and no more in all cases. So that's one scheme, a scheme that is flawed. It achieves compression, but it is flawed. And it's interesting, once you've seen something like that, to dive into a real scheme, a scheme that's actually been used and been put to wide use for a variety of purposes, to see what the designers of that scheme did to fight with the overhead problem and to solve things like the streaming data problem. And that's why in the next lecture, we are going to do just that.